Sorry. Bunch of new people. Thank you. Okay, hello again, everybody, and welcome to the second lecture of the DSP course. About the administrative stuff I have already explained. Just remember that you have to make it groups of 2 people, and for the homeworks and solutions, and send your solutions through email. You can find my email on the website, also in the first lecture. And you can type your solutions using LaTeX, or you can write down on a piece of paper and then scan it, but the scan should be with a good resolution such that I can read it. So, member of a group who has a better handwriting, it's better to write down the solutions, otherwise I will not understand it, and when I don't understand it means that you will not get the score. So, you can send it through scanning and sending it to the email. For the programs, you can use MATLAB code. My preference is MATLAB code, but still, if you have problem with MATLAB, which you shouldn't, because you're starting the signal processing, and from now on, MATLAB is one of the core programming areas that you have to deal with. For any research that you do, MATLAB is one of the best options. So you can actually write down your code, MATLAB code, but not to forget about the comments. When I go through the functions or any piece of any paragraph of the MATLAB, I have to understand what exactly you're doing. So at least one line for the comments, such that I can understand what exactly is going on in that piece of code. And that's it. So the first lecture we explained about the DSP theory, the subjects that comes under the umbrella of DSP, all the applications that it might have, some basics about the different areas. They are all connected to the DSP theory, but from different aspects, like multi-sensor, multi-resolution, source separation, and so on. Today, we are intended actually to go through the theory and really the basics of DSP. So we start with something that you might have already encountered in your signal systems, if you have already got the signal and systems course. Is anybody here that has not get the course of signals and systems, or anything related to that? You don't have? Have you already got it? Okay. So everybody knows something about signals and systems in a course. Good. It makes our task easier a bit. I don't need actually to explain everything by details. So today we are actually intended to go through the convolution sampling and the Fourier analysis, or better to say frequency analysis of the signal. Fourier domain is a kind of is a universe that all the elements are measured by the frequency. So that's why the frequency domain is also named as the Fourier domain. And let's start with some basic signals that we normally encounter in Fourier domain, or in discrete domain, in discrete domain. Exactly in the same way of what we encountered in the time domain as impulse response, or impulse, or delta, or Dirac delta functions, we have the same functions, or quite the same functions, in discrete domain. Because in DSP processing, digital signal processing, we are dealing with the samples. We need to know what kind of functions are normally used in this domain, in the discrete domain or the digitized domain. Now we explain some of these functions that are very important, because most of the other functions are based on these functions or can be defined based on these functions. The upper signal or the upper function is actually why I say signal and function, recursively. I just replace the names, because signal is nothing but a function. Signal is a function. If the free variable is time, then the signal is a function of time. So signal is nothing but a function. A discrete signal is nothing but a sequence. You know the sequence from the calculus, the basic mathematics? So when you talk about the sequence, you say that, for example, x of n for example, you say that x of n is a sequence with n changing from 1 to something, like t. What does it mean? It means that this is a sequence getting the indexes n as a free variable changing from 1 to t. So we have x1, x2, up to xt. So the indexes are belonging to the integer numbers. x1, x2, then xt. And these xi's or x of n's, actually they can get the value, for example, n r, the real numbers. In discrete domain, when we talk about the signals, we are not talking about something different than the sequences, which the free variable here, n, is somehow representing the intuition and the concept of time, with a bit different. That difference is, I'll explain. So, originally when we talk about the function in the discrete domain, we're talking about the signal in the discrete domain, we're talking about the function or a sequence with some index. And that index is a free variable that represents the time. And what is the difference? I said that there's a slight difference between what we have in the sequence or in the time, in the explanation of the time, and what we have here for the index. Why that is not 100% representing the time? Because it also depends on the frequency of sampling, which is hidden. If you consider a signal like this, if you consider a simple signal like this, which is analog over the time, and this is real, the time entity. So this really represents the time entity per second. And that's, for example, a sample of a signal. Analog signal varies over the time from some t0 to some tn. So the time continuously changes, and the same for the amplitude. When you take the samples, you're taking the sample every t seconds. So here is the first sample. Then you have, after t seconds, this t should mean a fraction of time, fraction of a second. For example, every 125 microseconds. Means if this is the period of sampling, so the frequency of sampling is 8 kilohertz. So if you take the samples every 125 microseconds, it means that you're using the frequency of 8 kilohertz of sampling. So every t seconds, which is this amount, you take one sample, and so on. So here it depends on t. But when you want to represent this kind of signal, the discrete signal, here, what you write down is, here you say x1 or x0, doesn't matter. Then you say x1 until the end, which is xn. Or it can be represented as x index 0, x sub 1, x sub 2, x sub n. That's the sequence. But you can confirm that there will be a big difference if I take the samples like this. So if the frequency of sampling changes, then x sub 0 until x sub n represent quite different values. So it quite depends on the period of sampling or the frequency of sampling, which are reversely proportional. But during representation of the signal in the discrete domain, we normally hide that. We ignore it. But ignorance doesn't mean that it doesn't exist. It is somewhere just behind of our and what we're writing it down actually. So we are somehow forgetting about the time or frequency of sampling, but it doesn't mean that it's not existing there. So when we talk about this discrete domain signals, it means that we have to take care about the frequency of sampling. That's an important thing. Even though it's a sequence, the same as what we have in mathematics, it somehow represents, the samples are actually representing the time samples, but that time is actually hidden. It is assumed to be known. I think you get the meaning. So we have the signals and functions. These are the things that quite, frequently I'm using the concept of signal or the concept of function, it doesn't matter. They are representing the same thing here in the discrete domain. So the function of unit impulse. So the upper function is actually the unit impulse. The unit impulse is defined as a value of 1 taken at the origin, which is 0, or the time 0, for example, and 0 everywhere else. Maybe you think that what is the use for such kind of signal or function? But later in the convolution theory, you will see that every signal, every discrete signal can be represented based on the scaled and shifted version of impulse function. Did you get it? Every discrete signal can be represented based on the scaled and shifted version of unit impulse. Any signal, any discrete signal, doesn't matter. So, assume that this is This is our discrete signal, x of n. If this is x of n, so you can easily write it down as, assuming that the signal ends here, and for example we don't have anything afterwards, so we can just easily write it down as 1 times x of n, tell me, plus 3. This one, 2 times x of n plus 2. 0. 0 times x of n plus 1. 4 times x of n. Oh, sorry, minus 1. It's dropped here. Minus 1 times x of n plus 4 times x of n minus 1, and so on. So what do you see here? Sorry, instead of x, I have to write down delta. Replace all the x's with delta. So we see that this signal x of n can be easily written as scaled these are the scales and shifted versions of the impulse function. That's why x of n in general can be written as ak delta n minus k. Ak represent the coefficients, and delta is nothing but unit impulse, and k represents the shifting amount, and this shifting amount is actually what you can see over the sum as a variable of the sum, summation or integration. That's the importance of unit impulse function. And then we have the bottom function, which is the unit step function. The unit step function is also the same as the other functions, can be written as the superposition or the scale shift versions of unit impulse. And these are important functions, basic functions in this discrete domain. We can see that unit impulse is actually the difference between the unit step and a shifted version of the unit step. On the other hand, delta of n is a derivative, the first derivative of the unit step. But we know that the derivative in the discrete domain is actually nothing but a difference. The difference in the discrete domain represents derivative. Did you get the meaning? So here un minus 1 is actually a derivative, but derivative in the discrete domain is nothing but equivalent to so if I want to write it down in the continuous time domain, I can write down like this. The first derivative, d of u of ut over d of t. But in the discrete domain, the equivalence is u of n minus u of n minus 1. Okay. I actually explained this slide by the example on the table, on the blackboard. So here, for example, we have a minus 3. These are the coefficients which are 0. And this one comes at delta n plus 3. Then we have something in L delta n minus 1. Then we have something here, which is n minus 2. N minus 1, n minus 2. Then 0 until n minus 7. And that's nothing but the summation over. Here I've called them xk, doesn't matter, xk or ak or x sub k, whatever. That's just the scaling. Yes, please.
The unit impulse function is represented as a derivative, and the derivative is calculable using the forward difference here. Right?
Yes.
So is there a significance of this, or we can use like any difference, like central or
Any difference. Any difference.
In that case, then the unit step function would be different.
Use a central difference, you won't use it.
You can use any difference with the same scaling. If they have the same scale, you can use any differences. So un minus 1 or un minus 1 minus un minus 2 or whatever. Even the non-causal version. So un plus 1 minus un or un plus 2 minus un plus 1. Whatever. Doesn't matter. But there is a forward version and the backward version. Also, there is a causal version and non-causal version. So here, I have written something in the causal version using un and un minus 1. That's not a problem. But if you use n plus 1, for example, then un plus 1 is non-causal because you're having something starting before and going to the, before we know the signal, you have some value. And that for the discrete case is not a problem in general. But for because I wanted to make something equivalent to the time domain, the real time domain signal, I just wrote it down in this way. But in discrete domain, we have more flexibility that you will see in the, yes please.
Like you said, when you use the central difference, you will have an issue. Where if you take n plus 1 and then n minus 1, that will not give you this response.
N plus 1 and
N minus 1.
n minus 1 is quite different. You have two samples in between. N plus 1 is here,
Yeah.
n minus 1 is here.
So that's what it won't work. So you have to take only forward and backward.
Yeah,
Forward-
exactly.
Yeah.
Just one difference.
Yeah.
One difference. Okay. There are different other basic functions that are useful in the discrete domain, and they have some equivalences in the time domain. You have already seen those functions. For example, when we talk about the exponential in the time domain means that e to the power of something. In the discrete domain, when we say exponential, we mean this, alpha to the power of something, n, for example. But depending on how alpha changes, you can have different types of signals. For example, if alpha is greater than 1, then what you see is left-hand corner, and it's just monotonically increasing. If alpha is between 1 and 0, then it's damping. So it's coming from greater value and then just damps down. And if it's between minus 1 and 0, it's just frequently changing the scale, the amplitude from positives to negatives, but also it's damping. You see that it's damping, converging. And if alpha is less than minus 1, it's diverging. And again, fluctuating between the positive and the negative values. But it's diverging. So that's the meaning of exponential in the discrete domain. We have the concept of frequency. The concept of frequency is almost the same as what we had in the time domain, with the bit difference. In a time domain, when we talk about the frequency, what do we mean? In the frequency, the time domain, when we talk about the frequency changes from 0 to infinity. Is that right? So in the time domain, when we say that x of t is a signal, for example, is a cosine of omega t plus some phase, initial phase, for example. Initial phase that mostly is represented by phi of sub 0 or something like that, or a constant value. Here, this omega, which normally in the analog case, for those who are studying telecommunication, normally they show this with this omega, Latin omega, like this. This omega, it can change from 0 to infinity. So that's the omega. And the signal, for example, here is a cosine signal with a previously known omega. It should work like this. If you increase the omega, then it means that the signal is more compressed. And if you increase the omega to infinity, what you actually have is, so the period between two peaks that come right afterwards gets closer to 0 when omega goes to infinity. Is that clear for everyone? But in the discrete domain, when we say the minimum frequency, we're talking about the radian. I mean, that's quite different in the sense that it's represented by omega in the discrete domain. When we talk about the lower frequencies, we're talking actually about the 0 frequency or 2 pi, or any multiplications of 2 pi. And when we talk about the highest frequency, we're talking about pi or not the multiplications, but odd multiplications of that. So it's the angular frequency. So the omega in the discrete domain actually is nothing but rotation over a unit circle. So the minimum frequency happens here, and when you just round the circle and come back here, again you are in the minimum frequency. But the highest possible frequency happening here. So when we talk about the highest possible frequency, we're talking about pi. When we say lowest frequency, we're talking about 0 or 2 pi. And the way that we can see that is, for example, when you have 0 or 2 pi, it means that every sample is happening right afterwards with the same sign. But in pi, we are actually having the most fluctuations possible. So we fluctuate between the positive and negative values right afterwards. So it means that this is the highest frequency possible. Frequency is the amount of fluctuations that you might have. And here you have the highest possible fluctuation. So that was the concept of frequency. And we have some concepts for the system. Just the same way that we have for the signal, we have some noun concepts for the system when we talk about the discrete time domain. We have in the signal and system, you have already seen about the linear time invariant systems. Linear time invariant systems, which you call it LTI. There are some properties assigned to the LTI systems. Quite similar properties should be assigned to the LSI systems, which are linear shift invariant systems, the equivalent of LTI in the discrete domain. So, linear time shift invariant systems, or LSI systems, they are represented like this. You have an input, a signal like x of n, which is a sequence. It passes through a system with a transfer function of t. So t applies over the signal, and then outputs a signal like y of n. A transform or a mapping from input function to the output function, from the domain to the range. The shift invariant system should have at least these two. At least, I will explain it later, why I said at least. They should have these two properties, the linearity and shift invariance. Linearity, what does it mean? Linearity comes with two properties. One of the properties is called homogeneity. That means if you have x of n, x1 of n applied to the system, you will get y1 of n. And if you increase the scale or decrease the scale by the coefficient of a1, so if you apply a times the input, you will get a times the output. It's called homogeneity. And also it has the property of superposition. So if the input comes with x1, or in general, if we generalize it to the homogeneous case, which means a times x1, plus b times or a2 times x2, then the output would be a times y1 plus b times y2. That's called a superposition. So LSI systems are in general linear, which by all means, in turn it's a combined property of homogeneity and superposition. And also it's called shift invariance. It means that if the input starts at any time, for example, in the normal case, x of n starts at the 0 time, then the output starts at the time, exactly 0 time, or a delta difference, because normally we have no system that just immediately after you give the input to get the output. There would be a difference at the time shifting or the time delay that the signal goes through the system, and then the system starts processing the signal and then outputs something. But ignoring that processing time, if we mean that immediately after giving the signal, the output is given, so it means that if signal is given at time n minus n0, then the output should be given at time n minus n0. It doesn't necessarily mean that if it doesn't care about the time that you give the signal. It means that any time that you give the signal, the delay to give the output is quite constant. Doesn't matter whether you started from the 0 time or time 5 or time 10 or whatever. That's called the linear shift invariant system. It's the general and broad family of the systems in the discrete domain, and they are frequently used in these DSP systems. So if you have the impulse, unit impulse delta, then you get, for example, an output which is called impulse response, which is normally revealed by h of n. It means that shifting the delta will give you the shifted version of the impulse response. There are some examples for the systems normally used in the DSP theory. One of the very prevalent examples of this linear shift invariant systems is called actually the moving average. Moving average. Moving average is actually taking the average over the samples. But the size of the window, which is considered to take this average, depends on the parameters of M1, for example, here, and M2. And what are these M1 and M2 is nothing but assuming that this is a signal that's changing across 0 time, and it starts from, for example, M1 and ends by M2, then the size of this is nothing but M1 plus M2 plus 1. So that's the size of this window. So if you just put a window here, a rectangular window with the size of M1 plus M2 plus 1, this is the number of the samples that are located and placed inside this window, rectangular window. Just sum up all the values that you have, sigma over the values that you have from minus M1 to plus M2 or whatever. So you add up the samples and take the average 1 over this. So that's moving average. Why? Because you can keep this window fixed and you can just move over the time. So by evolution of the samples over the time, you keep the size of this window fixed, and you just, by getting any new sample, you just move one sample forward. And again, take the value, take the average. Example of that would be shown in MATLAB. Just copy and paste it into the MATLAB and run it. And then tell me what actually moving average does. Can anybody tell me now? No. If you have a high frequency signal, a signal which has so many fluctuations, and then you do, for example, a moving average, what happens?
It smooths it.
Exactly. Who said that? That does smoothing. So moving average is a kind of low pass filter. Great.
I mean, this is similar to applying a Gaussian, right?
You can put a Gaussian, but moving average is nothing but just a simple rectangular one. You can have a Gaussian. If you do the Gaussian, then it's not calling the moving average. What you say is windowing. That's called windowing. You can have different types of windows. For example, in short time Fourier transform, you use for example, the Hamming window or Hanning window or Kaiser window or whatever. But simply taking the rectangular one is called moving average. Use this example and you will understand exactly what's happening. You can change the values, you can change the filter. Here, I actually manipulated the coefficients. So you can fix these values all to 1, then is standard moving average, and if you change these values, it's a low pass filter. Yes?
Someone said it's convolution, it's still true, you're just multiplying the same average, single value, it's the average value that you're converting to. So
it's true,
you can call it that.
Convolution is a very general meaning, and it doesn't represent what actually moving average means.
Yeah.
But any kind of filter is a convolution. When you pass the signal through any system, what is actually happening is a convolution. So I said no, it doesn't mean that the answer was wrong. It means that the answer is not complete. And now what you mentioned, convolution. Please.
Moving average, is it similar to the box filter, or is it the same thing? Same thing.
And you have box filter as multiple dimensional moving average. For example, you have two-dimensional box filter. Yeah, that's true. You have different names for many of these. So let's talk about what you mentioned as a linear convolution. And I'm insisting on linear convolution, linear, because we have another type of convolution just coming after we talk about the DFT, and it's called circular convolution. So I'm not talking about the circular convolution, but it's linear convolution. So we already saw that if we apply the unit impulse to any LTI or LSI system, delta of n, the unit impulse, will give me the impulse response. Response to the impulse. Impulse response. By itself, it has originated as a name. So impulse response for a system means if you give an impulse, unit impulse, what is the response of that system? And it is shown by h of n. I already explained that every discrete time signal, like x of n, can be represented by scaled, shifted versions of the unit impulse, as it's mentioned in the upper formula. Now what happens if we apply this x of n to the system? And the system is already known that it's linear shift invariant, LSI system. If we apply x of n, then this transfer t is applied over the entire signal, which is x of n. Then if the system is linear, it means that you can replace the transform and the summation. Why? Basic mathematics. If you have dozens of linear transforms, integration, derivation, any function which is linear, any linear function, if you have dozens of that, tons of that, condition then, there's a condition. If whatever inside that argument, as an argument, is converged, so if the argument is converging, it's not diverging. If the argument converges, or it's stable in the meaning of bounded input and bounded output stability, it has this kind of stability, whatever number of these, operators which are linear, you can replace them. So summation is a linear function. Transform is supposed to be linear transform, LSI system. You can easily replace them. Provided that here you have something which is stable, or bounded input, bounded output stability. That's kind of property you should have. Then you can replace them and you get this. So by linearity, t goes through and just apply to this delta function. And we already saw that delta function gives me the impulse response, or h of n, and we know that it's shift invariant. So shifting of this will give me the shifting version of h of n, which is h n minus k. So using the linearity and the shift invariance properties, we see that the output is nothing but a scaled, shifted version of the impulse response. This is the impulse response, because it's a response of delta. So this is the impulse response. As we had for the signal we had, it's the shifted scaled version of the delta. Here you have the output of the system, which is LSI, is the scaled shifted version of the impulse response. And this representation is nothing but the convolution. So it means that if you have any kind of system, or as you mentioned, filter, that's not a problem. System or filter, whatever, when you apply a kind of input, the discrete input, the output is nothing but convolution of the input and the system. the convolution of the input and the system. And that's really interesting and important, because it means that if you know the impulse response of the system, if you know that already, you should know the response of the system to any input. If you know this, the filter is not changing. That's the system. It's already fixed with any parameters. You set the parameters. That's all. After tuning the parameters, you just let it go. And input is coming. Stream of input is coming. If you know the system already, then by knowing the input, you should definitely know the output if the system is linear shift invariant. That's the beauty of the linear systems. And that's why people in mathematics and many other fields of engineering, they try to model every phenomena, every natural phenomena, even by the linear systems. Because only linear systems have this property. If the system was nonlinear, you couldn't say such a thing. But here, by knowing the input, you can uniquely define what should be the output. And the other way around. If you know the input and the output, and the system here is invertible, you can uniquely define, if you have the output and the system, which is invertible, you can uniquely define what should be the input. You can have the inverse of the system. And that's only the property of the linear systems. That's why we go through the linear systems in most cases, unless there's no other choice. So, we're showing everything in the convolution system, in the linear convolution case. So we see that x of n applied to the system, which is LSI, we get the impulse response, which is a convolution of these two things. And we have to know that convolution as a linear operator is also permutable. So you can easily permute the place of x of n and h of n. As a linear operator, you can easily permute these things. That's why the concept of signal and system, in many cases, they are used in their place. Sometimes you see that in the literature you're talking about signal. You see something about the signal, but then it changes to system. And frequently you see this kind of changes between the signals and the systems, because of the concept of convolution. You can easily change their role. So for the classification of different types of systems, we can go through these topics, these classes: the linear systems, causal systems, stable systems, memory having systems or memory-less systems, invertible systems or non-invertible, and shift invariance, which we talked about. When we say invertible systems, what does it mean actually? It means that you can find another system which is called inverse system if you apply the output of the first output, which is, for example, if you have here x of n and here is h and here you get y of n, you should find a kind of system like G that gives you back x of n. If such a thing can happen, it means G is H inverse. And this system is invertible.
But is that possible?
Yeah. It is possible. It can uniquely be possible if this system is, later we will see, minimum phase. If this system is minimum phase system, That can uniquely happen. So you're pretty sure that such a system you can find it. But if it's non-minimum phase, then you have different alternatives. Probably you can find an inverse, but maybe that inverse is not unique. Yes?
Is it the deconvolution process?
That's the convolution. Is actually you're deconvoluting the effect of the system is actually removed.
I think that's a dangerous process, right? Doing deconvolution. I mean, like, is this the one where we're doing de-blurring kind of stuff?
Deconvolution is a more general idea. It's the basic idea that you can get from the deconvolution is, yes, you're getting the inverse of the system. You're somehow getting the inverse of the system or equalizing the system. Have you heard about equalizers in the telecommunication? Yes. Equalizers are actually the deconvolution. They're doing the deconvolution. Have you heard about the source separation, blind source separation? Blind source separation is nothing but a deconvolution. But when I say in a different sense or a more general case, because it's not that much easy that you think here. Sometimes they go through the dictionary that the signal is made from. They make an over-complete dictionary, then using irregularizers and some prior knowledge, they try to extract out those atoms of the dictionary which are more likely that the signal to be created from. And that differs from one frame to another. So that's why it's not just as easy to say that, okay, I found the inverse of the system. No, it's not the inverse of the system. It's the best approximation of the system for that moment. Okay, and for the case of the signals, we have continuous time, discrete time signals. We have periodic and non-periodic signals. I think it's easy. Everybody knows that. For example, a cosine can be periodic. We have band-limited and wideband signal, or I think it makes no sense to say, band infinity signal. There should be no signal with infinite frequency. So, because it saturates or explodes, one of these two cases. So we have band limited. It means that the signal is bounded in a frequency range from f1 to fn, like every signal that I know. And we have real signal and complex signals. Real signal, like the speech signal, is real in a time domain. There are very nice properties assigned to the real, complex, and these kind of signals, or analytic signals. What are these nice properties? I just say as a short and brief explanation, just to give you the flavor of what does real means and the complex means. We will see later in the Fourier analysis that when you have real signal, if you have a real signal, then the frequency spectrum of the signal is symmetric. So if you have x of n, if x of n is real, then whatever you have in the positive frequency range, exactly symmetric to that you will have in the negative frequency. So the spectrum of the signal is symmetric. And what is the advantage? When you do the modulation. Yes?
Half of the information is redundant.
Exactly. So you have, when you do, for example, the frequency modulation. When you do the frequency modulation, half of the information is redundant. You can just simply take one side. Instead of double side, you just take right-hand side or the left-hand side and you modulate the signal. That's belonging to the telecommunication. I don't want to explain that. But just for your knowledge. Yes?
Any example that I could think of, like image domain, audio signals, whatever, all these are real signals. Where does the complex signal come out?
Light.
Okay.
Electromagnetic signals, they are complex signals. They are two orthogonal signals, one electricity and the other magnetic, and they are complex. So light, when you want to show that, is xt plus jy t. This is the electricity and this is magnetic. That's a sample.
Fourier transform of these things, I would actually have complex values too. It won't be zero, so I'll have to play with that too.
Exactly.
Okay.
If you have a complex signal, definitely you will have a complex Fourier domain. If you have a real signal, again you will have a complex Fourier domain. But the spectrum is symmetric. For this case, it's not symmetric. And you have analytic signals, and the analytic signals are the signals which have no negative frequency values. So this part vanishes. There are signals which are analytic. You don't need to go through that. These are just for your knowledge. You have power signals and energy signals. I think it should be clear in the name. When we say power signals, it means that the energy is exactly. So the power signals are those which their energy is just definable in a period. In a period of time, the energy is something known or limited, but if you increase the time, then the energy goes to infinity. But the energy signals, they have limited energy. Okay? So now tell me, the cosine signal, is that the power signal or the energy signal? Exactly. And we have the deterministic signal versus random signal. I already explained. Deterministic signals are those which you can define just by the formula and one initial point. That's enough. For the random signal, you cannot predict them, but the amount of randomness differs from one type of signal to another. You might have fully random signal which has the probability distribution of which of the distributions has the most randomness?
Gauss.
Exactly, the Gaussian one. And if you just get farther from the Gaussian, you will definitely, your entropy starts decreasing. It means that you have a kind of information inside the signal which is already extractable. Because entropy is the measure of information. So the Gaussian signal has the most entropy. It means that it's the most non-predictable signal. So when you see in the telecommunication that people talk about the white Gaussian noise, WGN, why do they talk about the white Gaussian noise as the additive noise to the signal? Because if they can solve the problem for the white Gaussian noise, they can solve for any other type of the noise. The worst case noise is WGN. Okay? Let's move into this sampling. So the first idea of sampling came with continuous to discrete. So you have the continuous signal, like this blue one, and then you take the samples. As I already mentioned, every t period of time, you take one sample. And that t depends on the signal. Later, we will define a measure, how to figure out, how to set this t to a proper value. But initially, assume that we have something appropriate for the t, already set. And now we get the samples, x0, x1, x2, and so on. These are the values which are still real values. They have not changed to something like the bits or bytes something like that. When we come up with a byte of the signal, a byte or a word or some bits that can represent the amplitude of the signal, then our task is finished for the case of sampling. So the first step is continuous to discrete conversion with a known frequency. So you get this sequence of the values. Then you need to do the quantization. So depending on the number of the bits that you want to assign for the quantization levels. If you have 3 bits, it means that you have 8 levels. If you have 8 bits, it means that you will have 256 levels of quantization. So every signal which is crunched into the dynamic range of, for example, 0 to 1, if you normalize, assuming that the signal is already normalized between 0 and 1, it means that all the signal and the details of the signal, all the movements, fluctuations over the signal, they all, when you take the samples, should be in the range of 0 to 255 if you have 8 bits. Yes?
So, I mean, if I want to sample it, it's easy. I just have to multiply with the delta form for a continuous signal.
Okay.
But what would I multiply with for a quantizer? Like, how would I say, like, this is somewhere in the range of 5, this is somewhere in the range of 10, this is somewhere in the range of 255?
It depends on the dynamic range of the signal. We have to already know what's exactly the dynamic range of the signal. So one of the basic tasks that every engineer, the DSP engineer, should know is that you have to initially know about the dynamic range of the signal. You should know that your sensors, what is actually the dynamic range that the sensor actually provides the signal for you.
Okay, I mean, okay, so like in an image, it's usually 0 to 255. I know those values. Now, how do I say, like, for the incoming continuous signal, like, I mean, I have a setup like this, and then how do I say this value has to be 5 or this value has to be 20?
You should, limit the signal, the input signal to a known limit.
Okay.
So you have to use using any kind of analog inverters or any kind of, for example, if you have a kind of sensor, if you're using the speech as a signal and then you have a microphone, that microphone has some limitations for the amount of voltage that it can give you in the input. For example, the company gives you the catalog for that microphone that it gives you the input signal from 0 to 5. So what does it mean? It means that whatever the volume of the signal it is, doesn't care. It just goes between 0 and 5. If you want to do any kind of amplification, you have to do it inside the processor. But then it would be definitely different tasks that, for example, it gives the input signal is coming from 0 to, assuming that the offset is more than 0. It comes from 0 to, for example, 15 or 50 volts. It means that the dynamic range is between 0 and 50, and you have to do something with this range. Now, it depends on your applications, whether, for example, you have a basic or prior knowledge that people normally, when they talk, the amount of volume that comes is in the voltage of the range of 15 or 10 volts, and it's not more than that. Unless the people start shouting or screaming. Then it goes beyond, for example, 30 volt as the input. Then you have to create a kind of circuit, electrical circuit, to somehow saturate the voltage in some level, or linearly or non-linearly, depending on your application, to map the signal from that range to to a lower level of the signal. So that's called the level shifting. In analog electrical circuits, they say the level shifting. So you do the level shifting, and then when you are in a certain range which can be used for an A to D converter, then you give it to the A to D converter. For the speech case, if you use these capacitor-based microphones, these capacitor-based microphones, they are between 0 and 5. And when they output any signal, that's between 0 and 5. And it's completely matched with every A to D chip that you use it. But the point is that inside the A to D, even because of some, importance that, for example, a kind of level has with respect to another level. For example, the higher levels doesn't have that much importance, but something between 0 and 3, that includes mostly, the information. What they do is they exponentially, they try to compress it, and that's called the ALA or MULA standard. The American version is called ALA. American standard is ALA. And the European version is called MULA. So that exponentially compresses the signal. It means that it will finally assign less number of the bits to the higher levels and more number of the bits to the lower levels. And this kind of quantization, then it passes through the A to the converter, and then you can, deal with it as a byte or word, depending on the A to the converter level. We will explain about that a little later. But in general, we have the continuous to discrete, and then finally we digitize it based on the quantizer and the quantizer levels. So here you see that after you take the samples, then you have the quantization levels. That depends completely on the range of the number of the bits that you can assign for the quantizer. The samples that you take will be assigned to the level which is closest to. So the closest level, the sample will be assigned to that. It means there will be a kind of error here. That error is the real sampling value subtracted by the value which is assigned based on the quantization. And that's called the quantization error. That's called the quantization error. And whenever the error happens, it means that error is a kind of signal. It's a kind of random signal. It can be like a noise. Then, whenever error happens, you have a signal and you have an error. Error is called as a signal itself, but a noise. Then you have SNR. The intuition of SNR comes up. Whenever you have error, the intuition of SNR, the concept of SNR comes up. So for that error, we have a definition of signal to noise, which is this error ratio. And that's the energy of the signal to the energy of the noise. Energy of the signal, the variance of the signal, or the energy of the signal. For random signals, normally the variance is nothing but the energy. So it's the variance of the signal over the energy of this quantization. But this quantization level, if you know how many bits you're assigning for the quantization, is something that you can pre-calculate it. Next slide, I will show how to pre-calculate the noise of quantization. So for every quantizer, we have parameters to set. One is number of the bits that you can assign to the quantizer, 8 bits, 7 bits, 16 bits, 24 bits. These are the standard number of the bits for the standard chips. There are chips used as A to D converters, just with, for example, 8-bit, 16 bits, or 24 bits, or whatever. And another parameter which comes from the dynamic range of the signal. So how many delta values, which are the quantization levels. Every delta is the quantization level distance from one level to another. So these are the parameters, and then finally, when you quantize, then you put it inside the bit, so it means that the signal is encoded in a byte. The amplitude is actually encoded by a byte, and that's the byte which is coming out of the A to D converter. But how to compute that is in this slide. We assume that this error of quantization is actually a unified distribution, having a unified distribution. We know that the level of this error would be between minus delta half up to the plus delta half. The delta is the entire level of quantization, so the error should actually vary between these two levels, which is from minus delta half to plus delta half. So the error is actually varying over this domain. And because it's a unified distribution, it means that the surface below the value should be 1. This surface should be 1. And this is nothing but delta, so it means that here you have 1 over delta. It's clear? It's a distribution. Because of the distribution, it should sum up to 1. It integrates to 1. On the other hand, we know that the delta, when you have dynamic range, so based on the b, we have 2 to the power of b, number of the levels, and we have the signs, plus and the minus, so we just subtract 1 to show the sign. And we have the dynamic range of the signal, which is coming in the input. So that defines the delta. And the energy of this noise, which is coming from this probability distribution, is varying over the minus delta half up to the delta half of this energy times the probability of that energy. Definition of the variance. If you define the variance, it's nothing but this. The energy times the probability of that. So the probability is actually the weight or the gain that you should assign to the energy level, the error level. Now because you know already this P of E, which is 1 over delta. So you just put it there. And it's based on the definition, which is clear, definition of the unit distribution. This variance is nothing but delta square over 12. If you replace the delta from here, that energy is actually computed like this. This is the energy of the signal, the error signal, I mean, the quantization as an error. That's the energy belonging to that. And if you put that energy into the previous formulation of SNR, if you put it here, then by assuming that, for example, if you assume the dynamic range of the signal is not more than 4 times the variance of the signal. This 4 has a meaning. In statistics, there is a kind of theory that says it rarely happens. It's something that rarely happens, that for real signals, the dynamic range goes beyond 4 times the variance. So, based on that, if you assume, for example, that the dynamic range is 4 times the standard deviation of the signal, and you put it there, based on the SNR, if you put it there, then you will see that the SNR is simplified to almost 6 times the number of the bits minus 1.25. What does it mean? It means that with 8 bits A to D, you can get the SNR level for the quantization. You can get the SNR level of 42 decibel. It's the upper limit of quality of the signal that you can get. It means that if somebody is using 8 bits A to D in a system, like the telephony system, speech application system, enhancement system, and then finally the guy claims that he has got the SNR more than 42 dB, he's lying. Because even considering that all the processing of the signal the entire circuit and the processing and everything is doing perfectly, everything is done perfectly, if it's like that, just because of quantization, the level of SNR, the upper bound, is limited to 42 dB. And definitely you will have a lot of errors inside the processes that will decrease the level of, the SNR from 42 to whatever possible. So that's the highest and the upper limit just because of the quantization level. So, on the other hand, it's approximately saying that for every single bit that you can add to the A to D converter, how much gain you will get? Almost 6 dB gain. Every single bit in the A to D converter will give you almost 6 dB of gain. 6 dB, the upper bound of the signal, SNR, will increase.
Should be 5 right?
Sorry?
So you subtract 1.25.
Yeah, minus 1.25. I said almost, so. About the dynamic range normalization, as I already told you, ALA and Mueller standard, the lower part of the signal normally contains more information than the higher part, the higher level parts, the higher amplitudes. That's why normally the exponential form of the normalizers, dynamic range normalizers, are used just to get this intuition that we can non-linearly assign the quantization levels. So when we use such kind of exponential form of the dynamic range normalizer, what we are inherently doing is, implicitly, is that part of the signal is more important than the other part. So the lower the amplitudes are more important. So here in the lower amplitudes, we are actually linearly changing in this dynamic range compression. But when we are, for example, more than 16 dB level, then we see that it's actually saturating. It means that more than this level, in the dynamic range, normally you don't have that much important information. So implicitly, if this is the signal changing from 0 to something, and the dynamic range is nothing but the maximum, the real maximum, to the real minimum, this is the dynamic range of the signal, then it means that for the lower part of the signal, you have more quantization levels, and when it increases, you are actually increasing the level of the distance or the level of quantization. So it means that, for example, any samples that are taken from here, 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 they are all assigned to the same quantization level, and the error is much less than uniformly distributing these levels of quantization. At least for the speech case, it works really well. And it's mostly because the signal doesn't vary that much. As I already told you, it's the 4 times dynamic range wouldn't be more than 4 times the variance. If such a thing happens, it means that it's because of the noise. And you don't want to quantize the noise. So, 2 standards for the speech case are called ALA and Mueller, American and the European standard. And we don't care about the formulation of those. Now, this Fourier analysis or the frequency analysis of the signals happen. This idea, I want to explain it with some very interesting slide and somehow a magic slide. You'll see why it's magic. Assuming that x of n, I'm talking about x of n, signal in time, if that's in the form of e to the power of something, e to the power of j omega 0 means a constant omega, the frequency, times n, which is somehow representing the time samples, if that's the input, based on the linear convolution theorem, y of n would be the impulse response to that input. And if you put the impulse response, because it's e to the power of j omega n minus k, you can separate these two terms. And if you take it out, because this term doesn't belong to the k actually, here, you know, I actually merged two operations to each other. So assume that e of j omega n, I take it out. Still we are dealing with k, but then I change the k to the n. So you can forget about that. Just consider it's k. But the point is that one term is actually coming out of this sigma, and whatever remains is actually sigma, for example, if it's based on n, h of n to the power of 1 minus j omega n. And that's called, I think it's clear that this is called the frequency response of the signal in the Fourier domain. We call it as a frequency response of the signal. So it's in the frequency domain. But the magic comes from this point that we gave the signal in time. We gave the signal in time. That's the signal in time, again here, times the frequency response. So we give the signal in time, but we get something in the frequency domain. The magic comes from this point. So we give the signal x of n, but we get y of n, which is in time, but it's y of n, which is time, the signal in time times this value, which is only belonging to the frequency. And the point is that time and time gives me the frequency. Why? Because the function is eigenfunction. Or they are called the atoms, or the dictionary of the Fourier domain. These are the dictionaries. One of the properties of the dictionary is that if you use an overcomplete dictionary and you give it to a system which is definable, something that identifiable in that domain, then the output is definitely a multiplication of that input. So e to the power of j omega n is an atom in the Fourier dictionary. That's why if you give it to a signal which is already identifiable in the Fourier domain, if you give this signal to the input, you will get a coefficient of that signal in the output. And that coefficient is something that represents the frequency representation of the signal. That's the property of eigenfunction. So for every eigenfunction, when you give eigenfunction, or in other way, if there is a function, you give it to a system, LTI or LSI system, and the output gives you a scaling version of that input, then that function should be eigenfunction. In this case, we give such kind of function as an eigenfunction, which is the atom in the Fourier dictionary. So all the atoms in the Fourier dictionary can be generated from this just by defining different omega values, omega 1, omega 2, omega 3, and so on. You generate all the necessary atoms in the Fourier dictionary. You generate it, but because all of them are the basis or the atoms in the Fourier dictionary, if you give them to this LSI system, the output of this LSI system would be the coefficient of that input. And those coefficients are spectrum of that system, spectrum of that signal, input signal. So you give this, you get a spectrum of that. You give them the other one, you get the spectrum of that. That's something that has been used by Fourier, Joseph Fourier, to generate and create a new domain as a representation domain of the time domain signals. And he called it as the Fourier analysis or Fourier transforms.
I didn't understand the second step. How can you take the e power j omega naught n outside?
Just
Because it,
change the values of the omega
no,
for any
the
frequency.
previous step.
No, it's different.
This one.
It's K.
Just forget about this. Assume that this is k, the same as what is here. The sigma just depends on k. But e to the power of j omega n doesn't care about k. It has no dependency on k. We can't take it out.
Okay.
We take it out.
Okay. Here it's confusing because you mentioned n is not.
Because I changed the variable, it's confusing. I told you already that I changed the variable, but doesn't, you know,
Okay.
you don't care about that. It's not the problem. We can change it. In any way, if it's k or n, doesn't matter.
Okay.
What you have here is independent of n and k both. So it's just something, a function over e to the power of j omega. That's called the frequency response. And you see that we gave this function in time, and we got the output in time as something times the function in time, one in the input. But this one just depends on the frequency. How might that happen? Just because this is the eigenfunction. And if you change these omega values, you will change this representation. So it means that this is now a new representation for these signals, these types of signals. And Fourier, Joseph Fourier said that every signal in the time domain can be represented as a superposition of this. So it can be, in the representation domain, can be written as superposition of this. Okay? Now, so starting from, this slide was the motivator for the entire Fourier analysis. So the frequency response, that h of e to the power of j omega, that frequency response is complex. It depends on the frequency and it's complex. So it means that it has a real value and it has an imaginary value. On the other hand, it has a magnitude and phase. The other representation is based on the magnitude, the absolute value of the amplitude, which is called the magnitude, and a phase, e to the power of j something. And that coefficient of j is actually the phase of the signal. And here we have an example like the shifted unit impulse. If you have the shifted unit impulse, then what's the frequency response of that? This dot means this h to the power of e to the power of j omega. Just for simplicity, I put dot here. This frequency response, based on the definition in the previous slide, here, if you put it here, instead of h of n, if you put it delta n minus n of d, then what you get is e to the power of minus j omega n d. So it means that if you shift the impulse, the unit impulse, what is the frequency response of that? I heard it. Shifting the phase. It just makes a shift in the phase. So that's just shift in the phase. Okay, that was an example, but you can go through different examples that come in the book. And here is another example coming for a sinusoidal signal. If you have a signal like this, x of n, a cosine signal, periodic, then you can represent the signal as the exponential term. and if you have the exponential terms, then you see that e to the power of j something is nothing but the basis or the atom in the Fourier domain. So everything input as a superposition of this would be something as a coefficient of that, exactly the same thing. So here you see that we have a coefficient. So a half here, a over 2, a half is a constant. You don't care about the constant in transformations, linear transforms. It just comes outside. On the other hand, e to the power of j phi is also constant, because phi is constant. It comes out. These are constants. You don't care about that. But this part is a basis function, eigenfunction. It's an eigenfunction or basis function. So whatever output should be a weighted version of that, scaled version of the eigenfunction. And this is the scaled version of this eigenfunction. We already saw that. The same thing happens for the other term. And I already said that every signal, based on the Fourier theorem, most of the signals or every signal in the time domain can be represented as a superposition of these eigenfunctions. So here we show an example. Sinusoidal or cosine function. We actually made a superposition of these two eigenfunctions with frequency positive, frequency negative. These eigenfunctions, these are constants, we don't care. These eigenfunctions will give me a scaled version of the same eigenfunction and a scaled version of the same eigenfunction. Again, reorder everything, assuming that h of n is real. We know that h of e to the power minus something is h conjugate of that. These are signal system theory that you already had it. You can reorder everything and rewrite it as a times the magnitude of this, cosine of this. So it means that if you apply any cosine signal to the input of an LSI system, the output is exactly the same thing with a bit of difference, the slight difference. One is in the magnitude, which is the magnitude of that system in the Fourier domain actually. The magnitude of the system is multiplied in the magnitude, and the phase of the system added here. Here is the phase of the system.
It's even mouse pointer.
Oh, really? I just can see it here. I thought you're seeing. Okay, no problem. I'll explain it once more. So, here you have the eigenfunction, positive frequency, negative frequency. These are constants. What's the output if the system is LSI? The output is the scaled version of this. Forget about that. This is just a constant. A scaled version of this and a scaled version of this. Reorder everything, rewrite it down, you will get this. The same way that we got this superposition, we'll get back to this. That's the condition that we use. For the real signals, that's something true. That theory, you already know that from the signal systems. So, look at this y of n and that x of n. What's the difference? Amplitude is changed by this scale value. Phase is changed by this theta value, which theta is nothing but the phase of the system. That's all. So if you have a cosine applied to any system, immediately you can say what's the answer if the system is LSI. And from the signals in system theory, you know that every signal in continuous time, in mathematician form, they said in Hilbert space. The Hilbert space comes with the idea of the Lebesgue integral theorem. We don't want to go through that. But these are all defined in the Hilbert space. Just for your knowledge. Don't care about that. Fourier says every analog signal, every real signal can be represented as a superposition of sinusoids and cosines. That's the, masterpiece of the Fourier. So, we already know that the sine and the cosine was the answer. If the system is LSI or LTI, we already know based on every input which is sine or cosine what should be the answer. And we saw that the answer depends on the frequency response. So that's what we get. We give the signal, recall from the continuous time transform. We already know that in the continuous form transform, if you have x of t or xs of t, doesn't matter, signal in time, then in the Fourier domain, if you take the samples, it's just replacing this t with nt. That's all. Okay? But the basis, the atoms, the eigenfunctions are nothing but exponential form. E to the power of j and something belonging to the frequency. Whatever. Positive or negative doesn't matter. Because for real signals, we know that it's symmetric. Doesn't matter. Negative frequencies or positive frequencies doesn't matter. So, the discrete time Fourier transform defined for the discrete systems as x with the argument of e to the power of j omega. Just completely the same form that we saw in the slide, in the motivated slide, h of e to the power of j omega. Just replace that h with x. So, the analysis form of the Fourier dt of t, Fourier transform, is xn times this basis. This minus here, I see that some of you might be confused with this minus. In the mathematical form, when you want to construct a signal based on the basis, that basis should be multiplied as a conjugate form. And the conjugate for exponential term is nothing but minus. So the basis conjugate, which the conjugate for the exponential term, like this, is nothing but minus. That's all. But you shouldn't be confused because of that. It's just the basis times scale. That's all. The value of the signal. So the value of the signal times this basis will give you the Fourier analysis of the signal, or the frequency analysis of the signal, and the frequency parameter is nothing but this omega. The minimum frequency for this omega is 0 or 2 pi, and the highest frequency is pi. That's the analysis. It means that when you want to see the signal of time domain in the frequency domain, you're analyzing the signal with this formula actually. But the reverse is also possible, because this transform, this Fourier transform, is a lossless transform. It means that it's completely reversible. So the synthesis form also comes like this. And we don't need to actually prove it. But it's very easy. I mean, I can claim that that's quite clear and obvious that this should be the synthesis form. Why? Because for the synthesis, you're actually going back from the frequency domain to the time domain. And you already know that when you analyze the signal in the time domain, what you're actually doing is that you want to take out the density of the signal, or the values of the signal, or how much from every frequency component is contained in that signal. Okay? You analyze the signal. When you analyze the signal, it means that you are actually interested in knowing how much from every of frequency components is already contained in that signal. So you want to see the signal by its frequency components, and you don't want to care about the time anymore. That's completely mapping from the time to the frequency domain. So it means that you're changing your eyeglass, changing from a glass which only looks at the time to another domain or another universe which only looks at the frequencies. So that's the meaning of the Fourier analysis. which completely goes to the frequency components and takes out the frequency values of the signal, how much from every frequency it contains. We know that the frequency in the discrete domain changes from 0 to 2 pi, or from minus pi to pi. So the entire period is nothing but 2 pi. When you say how much from that frequency, this is the range, how much from each of these frequency components, it means that the density of the signal in that component. So you're averaging over 2 pi. And by changing the W here, or the omega here, the frequency value here, what you're actually doing is that how much from this, assuming that this is the basis, that just represents the, that this, for this, what is the amplitude for e to the power of j omega? 1. So you don't care about this. The only thing remains is here. So you are summing over how much component of that frequency, which is represented here, you're having. For every delta omega, if you assume this is sum, for every delta omega, how much value you have it over the entire period. So it's somehow representing a density. The component, the frequency component of the signal. So you have a time domain signal. For this time domain signal, you're actually representing like this. It means that how much going from the minimum frequency to the highest possible frequency, which is nothing but over this period of 2 pi, you're actually trying to get the density of frequency components over this period of time. And you are actually considering for every delta of the frequencies possible. D of omega, how much is that possible? So it's intuitively you can say that x of n should be represented as such. That's the definition of the DTFT, but still there's a big problem. It's not the problem of Fourier, it's a problem that we need to have something that works in the computer. And the computer doesn't understand this one. Because you see here that the value of x e to the power of j omega, still there's a big problem with it. It goes from minus infinity to infinity. So still we need to have a sample. It's still analog. So the DTFT, even if it's a Fourier or frequency transform, but still it's analog. We need to digitize it. Or in other words, we need to take samples. So I will stop at this point by just giving you this hint that because DTFT is analog, we go through another sampling, which actually takes the sample out of DTFT, and that's called DFT. So DFT is nothing but taking the samples from the DTFT of the signal in the frequency domain, and that's something that you can use it in DSP. But it will remain for the next lecture, which is actually tomorrow, 10:30. Thank you very much, and if you have any questions, I appreciate to take it. Yes, please.
I have a question about the spectrogram that you showed in the last lecture.
It's different.
But where you showed the frequency spectrum over time, but we can take the spectrum from a single point, right? So do we take a window and then take the transformation, and that's
Exactly.
great.
So a spectrogram is the time evolved version of DFT. So you take the DFT of every time frame of the signal, and then you evolve over time. Go to the next slide, next frame. Take that frame just in that period of time. Take the DFT of that and represent it. So spectrogram is actually three-dimensional. It has time, frequency, and intensity. We say spectrum. Spectrum is only the frequency domain. It doesn't care about the time domain at all. So when you say the spectrum of the signal, it means that, for example, you take the entire signal and then you just study over the entire frequency components that might be contained inside that signal in the time domain. That's all. You don't care about moving over the time frames. But spectrogram is a multi-resolution analysis which tells you over the time, how it varies over the time, how the spectrum is varying over the time. It's a multi-resolution. It's different from spectrum. So you have the spectrum, you have a spectrogram. You're welcome. Yes?
Can you go to slide 30?
Yes?
Sigma x.
This is the standard variation of the signal.
Okay.
The square root of the variance.
Okay. Because when you were saying this, you said 4 times variance, so it got confused.
4 times standard variation.
Yeah.
Standard
Deviation.
deviation.
Yeah.
These are the theories in statistics, self-similar statistics, if you have heard about that. Self-similarity. There are too many types of normally when you have random signals, you have to make some kind of prior with that. Otherwise, if you consider everything is completely random, then you can do nothing. But you can take some statistics out of that, and you can say something about that. That's the theory which we talk about when we go through the statistical signal processing, SSP. Thank you so much.